And now we move to our last talk for today. Dr. Gómez Pérez is the director of the language technology research at Expert AI. He works in the intersection of several areas of artificial intelligence, combining structured knowledge and the neural models to enable machine understanding of unstructured data as an analogous process to human comprehension. He is a former Maria Curie Fellow. He holds a PhD in computer science and artificial intelligence. Of course, he regularly publishes in the areas of RA, natural language processing, and knowledge graphs. Today, he has a very interesting topic for us to discuss and to show the data hunger versus the knowledge bottleneck in language understanding, and we have to pick our poison. So okay. Please go ahead.
Well, I hope it's interesting. Let me see. Can you see my slides?
It's coming, yes. But
presentation mode?
Yes, presentation mode. Go ahead. Thank you very much.
Okay, thank you very much for the kind introduction. It's a pleasure to be here. Yeah, we want to talk about different challenges and different ways to address natural language processing and understanding. How we can do better than that.
I'm really sorry. Could you speak a little bit louder?
Oh, sorry.
Be better now?
Yeah, much better.
Okay, good. Okay, so yeah, what I'm going to talk about today is I'm going to give. This is going to be a story or a tale of two towers in artificial intelligence and NLP. So one of them is the symbolic tower, and the other one is the machine learning tower, and how these two different approaches to NLP have different advantages, have different disadvantages, and how we can put them together in order to deal better with language understanding and what challenges this entails. Okay. Sorry. Okay, so let's start with the machine learning tower. Here we have NLP models that learn from the data. So typically we have a lot of data which can be used in order to train these models in a unsupervised way or a supervised way. And it has very nice properties because, for example, the more data that we have, the better models that we will obtain. So this ensures the scalability of the model and also that we can have yeah, we can have a very comprehensive view of different ways in which the different phenomena related to the natural language processing task that we are dealing with can be presented. Actually, this is a very strong approach to natural language processing, and in many of the current benchmarks in natural language understanding and natural language processing, the state-of-the-art approaches are based on this in machine learning, deep learning, and things like transformers that where we already started discussing about them during the breakout. No? This is very important for this talk. On the other hand, these approaches tend to be data hungry. So, and this means that in many cases, you need not only data, but you need annotated data that can be used in order to train models in a supervised way. And this is expensive, and it takes time to collect all this data. They're also kind of a black box model, which you have an input and then you have an output, but you don't really know what is going on in the middle. And the more complex the model, the more performing the model, the more the black box it uses to be. This is also related to the next disadvantage, which is related to a lack of true understanding of real world semantics and pragmatics. Even though what the model does is to adjust to the curve and optimize for a particular result, we don't know if this is being done because the model understands the data, or because it is just it is just optimizing a mathematical function. And then also can be a risk of bias depending on the training data that we are using. So this has to be selected very carefully. On the other hand, we have the symbolic tower. And here we have some our models that NLP models that reason on acquired knowledge. And by acquired knowledge, I mean, for example, knowledge graphs, semantic networks, ontologies that have been populated. They are structured, they are explicit, and they are used as a basis for many tasks in NLP, like, for example, word senses, ambiguation. The advantages is that they don't need training, because what you have is an expert, is a knowledge engineer that does the modeling, implements these semantic networks or knowledge graphs and the rules that ensure inference. They are logically interpretable, because you can see what rules have been executed on what parts of the knowledge graph are relevant for inference. And there's also a nice amount of modeling tools available out there that ensure that you can do this modeling in a more or less comprehensive way. But on the other hand, here we also have disadvantages. The first one, the most important one, is the knowledge bottleneck. So this is, you get the expert, you get the knowledge engineer, and he or she has to decide what to model, in which way, and how to represent this model in a semantic network or a knowledge graph, which is not trivial. So as a consequence, many of these models tend to be brittle or focus on very specific parts of the domain, and so on and so forth. You have to do all this manually, in principle, even though you have tools. And the more data that you have, the more chances that you will have that to encounter corner cases, which are hard to model and generalize. And like I said, modeling can be time-consuming. So as you can see, there are no perfect approaches. Each approach has its own set of advantages and disadvantages. But how do humans really think? Well, actually, we do a mix of both. We learn from experience by looking at the data, and we also do reasoning. We have mental models with rules that provide us with some kind of inference in order to make a prediction that is not only based on the data that we are perceiving, but also in what we in the mental abstractions that we have been able to build during time. And here I have an example coming from the economic field, which is basically about predicting recession in the economy. So here you have to look at the statistics, but you also need to have a lot of experience in order to be able to use those statistics right. So how do we bridge these two towers? How do we put them together? Well, during these years, we've been working in different approaches to do this. The first one is what we call a dexyravo. And here in dexyravo, we combine machine learning and symbolic approaches in a way which is a little rudimentary, because what we do is we have a big corpus of text. We have a knowledge graph, and we use the knowledge graph to disambiguate the corpus and extract all the different concepts which are associated to the words. So here we are extracting not only words and representations from those words, but we're also learning representations for the concepts which are associated to those words and other types of linguistic and semantic information. And this is learned in a joint way at the same time, which has very nice properties in order to increase the quality of each of both representations of words, lemmas, and concepts. So this is one approach. This is one way to do it, and in the end, you get a vector representation of words, concepts in a single vector space, which is very nice in order to do reasoning afterwards, and to use this as the input to many machine learning-based models, like, for example, based on neural nets and these kind of things. But the real game changer in this field in the last few years are language models. And among language models, I would emphasize, for example, transformers. These have been key in the last 2-3 years. So the advancement based on language models has been dramatic, and we have a plethora of them these days, like Elmo, ULMFeed, GPT, GPT-2, GPT-3, and let's say GPT-4. BERT, Roberta, and so on. And all of them are more or less trained in a similar way, which is to perform language prediction tasks, like, for example, predicting what is the missing word, a mask word, in a sentence based on the context in which this word appears, or what is the next sentence that may come after a particular paragraph. The good thing is that by pre-training these models, then we can fine-tune them for other language prediction tasks, and this gives us increased functionalities, increased performance, but at the same time, it kind of reduces the amount of training data, supervised training data that we need in order to train those task-specific models. And we cover a lot of different tasks in NLP by using this approach, like question answering, natural language inferencing, paraphrasing, name entity recognition, many others. Actually, these days, language models, and particularly transformers, are at the core of a pipeline of any NLP modeling activity, basically. And they have become extremely popular. This is what we call the Muppets, because they have these names. We have Bert, we have Ernie, we have Grover, you name it. There's a whole plethora of language models based on transformers these days that are here to stay and will be the basis for future revolutions. But how do these things work in practice? How do pre-trained language models work in practice? Well, the idea is that we have a self-supervised stage where we pre-train the language model on tasks like a mass language model and next sentence prediction on lots of non-labeled data. So this is totally unsupervised or self-supervised in this case. Then what we do is to fine-tune the result of that process using a smaller domain-specific and non-labeled data. And finally, there's a supervised stage, which is based on fine-tuning that pre-trained language model using small label data for a particular task, like a question answering, semantic similarity, you name it. This is an example of one of these tasks, which is a semantic similarity. Here, basically, what we do is we take the proxy representation of the two sentences in the serialized token here up there to the left, and we have two sentences as an input, and on top of the output of the language model, what we have is a fully connected layer, which is basically tells us if these two sentences are similar, semantically similar or not. In order to do this, we need some label data, and in this case, we have the STSB dataset, which contains 4,000 pairs of similar and dissimilar sentences. But these are very general purpose sentences. So what happens if we need to do this in a very specific domain? If we want to calculate semantic similarity in a very specific domain? Well, this is something that we did in one of the projects that we have with the European Space Agency, and particularly in the context of the Open Space Innovation Platform. Here, there are a number of campaigns, there are channels, and what we want to do here is to apply semantic similarity as a novelty indicator for when a new idea comes, we can see how novel it is compared to previous ideas or previous studies, previous projects, and so on and so forth. So we try to model this as a semantic similarity problem. But we encounter a number of challenges, for example, technical challenges. If the approach is symbolic, how do we capture, for example, explicitly the problems and solutions describing the ideas? I mean, there can be infinite corners. How do we manually model each of these cases with a number of rules that give us the capability to do inference in that sense? And if we apply a purely machine learning approach, how can we put together a minimal ground truth data set for fine-tuning this semantic textual similarity task using a language model, a pre-trained language model under the hood? Because, like we saw, this data set that we use for semantic similarity is general purpose. It uses very general data sets, very general sentences. But here in the Open Space Innovation Platform, we have very, very fine-grained domain-specific sentences that we need to deal with. And it's not easy. The model doesn't capture it just the same. A way to deal with these kind of things is by using stronger and more domain-specific pre-trained language models under the hood. For example, in another project, we are working with the University of Strathclyde in order to generate a pre-trained language model, a transformer, which is focused on space. And this is what we call a space Roberta. In a meeting the other day, one of the ESA colleagues asked, what would you like to have? Would you like to have a lot of annotated data for fine-tuning, or would you like to have a lot of non-annotated data that you could use in order to train language models which are specific of the domain? And the answer is both. We need both. But if we establish things in a sequence, I would start with having the most powerful possible language models that we can then fine-tune for specific tasks in the domains. The thing with transformers and language models in general is that the more training parameters that the model has, well, the higher the capability to learn, to generalize, and the reasoning ability that we will obtain out of it. And this is great because it gives us more powerful natural language understanding models. But also, on the other hand, what we have here is that the more parameters that we need to train, the more infrastructure we will need to put in place in order to do this training, and the higher the training time we will need to invest in order to do the training of the models. What this poses as a challenge for smaller players like SMEs and academia to train these models, and also a growing carbon footprint, because this consumes a lot of energy. And so far, you can see that most of the more popular language models have been trained by very big players in industry, like OpenAI, Google, Facebook, and so on. And the thing is growing exponentially. I mean, we were talking about GPT-3. GPT-3 has a humongous amount of billions of parameters that need to be trained. How far can we go with this approach? Well, this is like kind of a brute force approach. So even though they are the beginning for this kind of revolution, we need to be smarter than that. We need to come up with smarter strategies in order to keep scaling. And right now, there's very interesting work proposing sparse transformer models, which are, again, unlike these other dense models, work with ways to reuse in a smarter way the models that have been trained in the past, or to be able to switch on and off different parts of the transformer network, so that you can focus on a specific task, the specific parts that are necessary when you are modeling specific tasks. So there's very interesting research in this area that we are looking at the moment. Like I said, related to the training of huge language models, there is an increasing worry about the large carbon footprint that this is generated. And actually, for a couple of years already, there are workshops and events like this, Sustain NLP workshop, which are focused on this idea. The question that we need to make ourselves is, how do we need to see this pre-training of language models? Do we need to see it as a huge waste against the climate and all this? Or can we see it as an investment? Because one, that we have pre-trained a model, we don't need to train again. Again, what we do is to fine-tune it for the specific tasks that we need to accomplish. So this is part of the discussion that we are having in this area. So all these different advantages and disadvantages take us once more to the need of coming up with hybrid models. On the one hand, we can have transformers, language models that capture how language is structured and how words are related to each other in actual language. And on the other hand, we have knowledge paths, semantic networks. We have ontologies that describe, from a semantic point of view, how the different entities, how the different concepts in a domain are related with each other. and they do it explicitly. So we've also been working on how to bring this together and how to come up with hybrid models that combine transformers and knowledge graphs. And this is an example of that we call transigrapher. The way this works is that we start with a word sense disambiguated corpus, in this case SEMCORE, or we can also use some silver standards because it's very expensive to come up with totally disambiguated corpus. Then we give the sentences in the disambiguated corpus, we pass the sentences through a language model, which provides an encoding for each of the words and concepts that have been disambiguated in those sentences. And here what we get is a contextualized sense embeddings, which corresponds to the encoding of those concepts in the sentences that have been extracted through disambiguation. The next step is that, of course, we will have a very limited amount of senses that have a representation associated to them by doing this. So we need to extend it, and we need to extend it by using a knowledge graph, again, the knowledge graph that we use for disambiguation, in order to propagate these sense embeddings through the hierarchy of the taxonomy of the knowledge graph. So, for example, if we have an embedding corresponding to a dog, to the sense dog, we know that, and this is represented explicitly in the knowledge graph, that the dog is a type of mammal. So if we propagate the embedding corresponding to dog to mammal, we can have an approximate description of what a mammal is using these embeddings. So we extend all these, and in the end we have a decent coverage of a knowledge graph that we can use then for tasks like word sense disambiguation once again. So in this case, the language model is bringing a representation of human language and how sentences are built from a syntactic and a semantic point of view. And the knowledge graph is a human engineer interpretable conceptualization of a domain. And by putting them together, we're trying to get the best of both worlds. In practice, this is proving to be very useful. And the hybrid representations that we are obtaining have been able to produce very good results in different areas, like, for example, in disinformation and fake news analysis on social media, where we usually have a lot of problems in order to find annotated data and do fine-tuning on of the pre-trained language models with this annotated data, because there's not so much annotated data in this domain, and it takes a lot of effort to do so. By using hybrid representations, we cover this gap by taking this information from the knowledge graphs. And very similarly, in other domains like the scientific domain, where we're applying this approach to improve machine comprehension of scientific textbooks and other tasks like question answering. Okay, so I'm concluding my talk here, and I would like to share with you the takeaway message and how we can actually do this. Takeaway message is that if we want AI, and particularly AI applied to language understanding, to become more general, more human-centered, explainable, context-aware, but also cheaper and safer to scale, we need to combine the two towers. And there's no one family going this way and one family of AI going in a different or opposite direction. There are many good things that we can do in order to address the limitations that each of the approaches have. For example, it's different research work at the moment, which are trying to use knowledge graphs in order to do data augmentation that could be used in order to do increase the amount of data that is available to train models using machine learning or deep learning approaches, and many other things. And I'm going to give you a few examples of what I think are things that could be done in order to reach the two towers, to combine the two towers. The first thing is to learn language representations that are not only based on words, but also leverage the linguistic and semantic information that is contained in the text, and also in particular knowledge graphs like WordNet or transigrapher, which are lexicosemantic knowledge graphs. And here we have approaches like dexyravo that I presented earlier, or ESRIN, that is Baidu's language model. They do something very similar in this regard. We also think that a way to address this is by pre-training domain-specific language models, like Space for Alberta, and adopting sparse language model architecture as opposed to dense architecture. And here I highlighted switch transformers and adapters as a way to do this. Also, another way to bring the two towers together is by embedding symbolic knowledge within pre-trained language model representation. Transigrapher is an example of this. NoVert is another one, which I didn't present earlier, but include here the reference. And finally, thinking of how humans learn, we don't limit ourselves to a particular modality. We don't limit ourselves to text. What we do is we learn from what we read, but we also learn from what we see, from the diagrams, from the images, from the pictures, not just language. And this is a line of work that we are pursuing in a different environment. And we produced last year a system that was called ISAC, Machine Textbook Question Answering. And here we combine vision understanding and language understanding so that we would be able to answer questions that had to do not only with language, but also with diagram understanding. You have to put the two modalities together in order to be able to answer the question. So thank you very much. That was the end of my talk. There's this book that we published last year with Springer, A Practical Guide to Harvard Natural Language Processing, where many of these ideas are also discussed in more detail. And also, please drop me a line if we are interested in these topics. I'll be happy to discuss with you. Thank you.
Thank you very much, José. That was a very, very interesting talk. I never realized how complicated languages are. Okay, we are almost out of time, but we have a question. It is from Red. Do we need such a number of billions parameters? When I speak and express myself, I am doing it right, but I am certainly unable to maintain that many parameters in my brain. I don't even have 1 billion neurons.
Yeah, like I said, this is very much the brute force approach, right? And we are still at the infancy on how to represent language using this kind of model. So the first way to do it is by throwing billions and billions of parameters. But we need to come up with smarter strategies. And what I mentioned before about switch transformers and also adapters is a step in that direction. We're going in that direction at the moment.
Okay. Thank you very much.